They are both related to each other and they're related to the combustion process. So I'm going to be talking about it. So what you're looking at here is carbon emissions from combustion processes. And these are two major carbon emissions, carbon dioxide and carbon monoxide. So we see carbon dioxide swirling around. It's emitted from cars, from fires, from industries, and so on. And they accumulate. Carbon dioxide accumulates over time. It lasts over 100 years. That's why we keep talking about it when we talk about climate. But also we see the other part, which is carbon monoxide, which is a good tracer for fires. For instance, if you look at this area where there are a lot of fires, depending on season, you will see a lot of emissions of carbon monoxide. So the next one shows you actually the other aspect of emissions, which is the particulate emissions. So you've seen this a lot. You've seen this image, this movie a lot, and I like it very much because it paints the color of the different types of aerosols, atmospheric particles. And, of course, the blue is the sea salt. The green comes from fires, biomass burning. The red is dust, and white is volcanic and industrial emissions. Let's go to the next one. So when we talk about the source of the fire emissions, you'll see this image that shows the seasonality. If you look at the dates here of fires throughout the globe. So, for instance, if we look here, this central part, actually Africa contributes more than 50% of the carbon emissions from biomass burning. So in the dry season in this part, you see a lot, and then it migrates south during the rainy season when the dry season starts in the south. So if we go to the next one. So so this is an example of that region I just showed you. You'll see a real natural color image from VIIRS on the Suomi satellite. You'll see the black dots. The red dots are the actual fire locations, and you'll see the smoke plume coming out of the various fire locations. So here, the smoke is mixing with the dust. You'll see the biggest dust bowl in the world called the Bodily Depression. So you can even hardly see the coastline here because of the mixing of the atmospheric aerosols, smoke and dust. Next one. We show another kind of burning. This was the large fire that occurred a few years ago. It's called the station fire that occurred in Pasadena, California. You'll see very huge, if some of you remember, and you can see that these kind of big fires can inject with the force that it generates the plume very high to immediately form clouds that we call pyrocumulus clouds. The next one. So we can see also the vertical distribution of the atmosphere from LiDAR measurements. This one is the CATS LiDAR on the space station looking at the atmospheric profile. Watch as it approaches this area of burning where you will see the distribution of the smoke plume in the atmosphere in the vertical distribution. So all of these things we can relate the smoke emission source strength as well as the height based on the measurement of the energy from the fire. Next one. So actually we measure the fire. What we show here is called the fire radiative power. That is the strength of the energy release, of the radiant energy release we measure from satellite. So this is from Moody's. This is for a particular, a particular day throughout the globe. Next one, please. So here we're able to use the magnitudes of this fire radiative power to be able to show where the larger fires occur, the most intense, and where the smaller fires occur, which actually can be used to infer the type of activity going on. For instance, agricultural fires are smaller, but they are more numerous across the globe. Next one. And what we have done here, like I told you in the beginning, is that we're trying to see how we can relate these two things that come from fires, energy and smoke. So here we relate measurements of the energy from satellite and the aerosols from satellite. And we derive what we call these emission coefficients. So what this allows us to do is whenever we detect the fire, measure the energy, we simply use this coefficient to multiply, and we're able to calculate right away the rate of release of emission of smoke particles, which we plug into models to be able to show where the smoke is going and what it's doing. Next one. So this is an example of what I'm describing now, where we simply, this is the energy measured, this is the coefficient we've derived globally, and we just make a simple multiplication, and we get the total emissions of smoke in the world. So this is just an example from Africa. So we also see these fires at night, but because this is daytime, this is nighttime of the various instrument on the NPP. During the daytime, of course, you see the smoke, so you can measure it. During the night, you see the fire, but you don't see the smoke. So the coefficient we've derived enables you to simply measure, or rather calculate the smoke emission rate even at night when you're observing the fires. The next one. So, well, this is, we do these things from satellite, but we also want to be able to validate them. So we are going to NASA's planning in conjunction with some other agencies, NOAA and the Joint Fire Sciences, to conduct a field campaign, airborne campaign, to validate this method of deriving these things. But so we wanted to do that. We had drones. We wanted to burn this pile here last week, but it was too windy. We didn't want to take a risk. So since we couldn't burn it, what we did, we got this fire pit. We lit the fire. We still flew our instruments, small instruments, measuring the energy and the black carbon in order to really, simulate the relationship between these two products of combustion. So we're going to do this when we get a chance. We're going to burn this pile in January, and then we're going to conduct further experiments similar to this in order to be able to validate what we're doing. I think this is where it ends. Thank you very much.